Good afternoon, and thanks for attending Cutting Tool Engineering's first Lunch and Learn event. I'm Dennis Spate, the owner and publisher of Cutting Tool Engineering, and I'll be serving as the moderator of today's 30-minute webinar. Before we get going, I want to point out a few things regarding the GoToWebinar platform we're using. Attendees should see a screen on their desktop that looks similar to this. I want to quickly point out the important functions of the GoToWebinar control panel that you see here. I'm going to zoom in. By clicking on this button here, you can collapse the control panel, the GoToWebinar control panel, if you want to. And to reopen it, you're just going to click on that button again, and it'll reopen. This part of the control panel displays the handouts available with today's webinar. These are PDF documents that you can click on to download. Clicking on a handout opens a separate browser window displaying the PDF file. You can download the file to your desktop from there. Finally, the questions panel here displays any questions submitted by audience members and any specific communications to the audience from myself. To submit a question to me or today's presenters, click in this area, this box here, and type your question. Then just click the send button right here. Your question will appear in the box above. And now on to today's webinar, a CTE Lunch and Learn focused on tapping in titanium, which is being sponsored today by EMUGE-FRANKEN USA and the Tapmatic Corporation. As I mentioned, I'm the moderator and host of today's event. Presenting today will be Mark Hatch, Product Director with EMUGE-FRANKEN USA. Mark is a threading tools and machining veteran with more than 40 years of industry experience. Our second presenter today will be Joe Gilliland, Applications Engineer with the Tapmatic Corporation. Joe earned his mechanical engineering degree from the University of Idaho and has more than 9 years of industry experience. Before I hand it off to Mark, I just want to note that today's webinar is based on the Thread Without Dread feature article published in this month's issue of Cutting Tool Engineering. The article, written by CTE contributor William Levington, relied on the expertise of today's presenters. With that, we will now hear from each of our presenters as they review and expand on the main elements of the article.
Hello, and welcome to the EMUGE-FRANKEN presentation on successfully producing internal threads in titanium materials by either machine tapping or thread milling. To begin, let's review the machining characteristics of titanium as it relates to the production of internal threads. Titanium is very tough and strong. Titanium is long chipping when tapped, and chip evacuation can be problematic. Titanium has very high elastic memory. Titanium is prone to cold welding, resulting in built-up edges. Titanium is prone to localized work hardening if excessive heat is generated in the process. The three primary thread production methods used in titanium are, first, thread cutting with a machine tap, which is a chipping process where material is removed by a spaced sequence of cutting edges which are continuously uncut. Titanium will produce a long chip formation with this method. Second, thread milling, which is a chipping process by means of interrupted cutting where material is removed by producing short, broken, coma-shaped chips. Thread milling is the ultimate chip breaking process. Third, cold forming with a machine tap, which is a chipless process where the material is displaced by pressure and flows into the thread contour. A split crest is produced at the minor diameter. Cold forming titanium is possible, but can be problematic to consistently produce true to gauge threads, especially as tool wear sets in. Also, due to the deformed split crest, components such as those for orthopedic medical or aero engine will not accept this thread form imperfection. At EMUGE, we highly recommend the use of thread cutting methods in titanium. Here we see a magnified view of a cold form thread with split crest at the minor diameter. With the noted thread production methods, EMUGE offers stock-ready tooling solutions for titanium in a wide range of thread types to include unified inch, metric, UNJ and MJ, STI, self-lock with wedge ramp profile, and taper pipe, MPT, and MPTF. Now we will look into the EMUGE titanium cutting tap program and the technology behind the exceptional performance levels achieved with this thread production method. The cutting tap program consists of two primary designs, one for blind holes and one for through holes that have been specially engineered for titanium. Here we see the blind hole design, which incorporates a 15-degree right-hand flute angle for optimized chip evacuation in the reverse direction, semi-bottoming chamfer, ground with HRG technology and TICN coated. More in a moment regarding HRG technology. The through-hole design has an advanced left-hand helical flute form and chamfer geometry which combine to optimize chip evacuation in the forward direction and add strength to the cutting teeth for enhanced tool life and process security. Also ground with HRG technology and TICN coated. HRG technology incorporates advanced high-relief geometry which increases space between the friction surfaces for enhanced lubrication and reduced torque load in both forward and reverse direction. HRG counteracts the high compressive forces produced by the extreme elastic memory of titanium. Successful tapping in titanium not only requires a specially engineered tap design, but also use of a tap holder that incorporates length compensation on tension and compression, whether the machine tool is equipped with an older conventional tapping cycle or newer synchronized rigid tapping cycle. Use of a length compensation tap holder improves tool life, thread surface finish, and gauging quality. EMUGE offers a full line of tap holder solutions for any machine type. When a workpiece shape requires a long reach to the hole position, an EMUGE precision tap extension can be used to easily extend a standard length machine tap. Core hole preparation by drilling has a strong influence on successful threading in titanium. The pre-tap core hole quality affects tool performance and gauging. Drilling-related problems such as incorrect hole size, bell mouthing at entry or exit, work hardening of the minor diameter, out of roundness, angular deviation, or misaligned hole will influence tool life, thread quality, and gauging. EMUGE offers a high-performance drill line for precision hole making in titanium. Successful tapping in titanium requires very high lubricity from the lubrication method due to the high compressive forces produced by titanium. Machining coolants are categorized into four primary types: synthetic fluids, semi-synthetic fluids, soluble oils, and straight oils. When using synthetic fluids, the concentration of oil content is a critical factor for the level of lubricity provided in the tapping operation. Higher concentration levels are essential for successfully tapping titanium. A tapping oil specially formulated for difficult materials such as EMUGE tapping fluid provides the highest level of lubricity. Now we will review the advantages of thread milling titanium. Eliminates the possibility and consequences of tap breakage. Easy machining of difficult materials. produces small controllable broken chips. One tool for through or blind holes. One tool for right hand or left hand threads. Pitch diameter can be controlled by CNC offset. Full bottom threading within one thread pitch of the bottom. One thread mill can produce multiple thread sizes. Does not require a high level of oil lubricity from the cutting fluid. Now we will look at a difficult threading application with special requirements that would have required a custom tap. To go beyond the limits of tapping in this challenging application, thread milling was recommended and supported by EMUGE. The thread call out is for a 1/2 13 unified special left hand. The special thread dimensions are oversized pitch diameter, minor diameter limits controlled to produce 75 to 80% thread height, and full thread depth controlled to 1/2 turn. Additionally, because of a finished 30-degree taper bore at the hole's bottom, a drawing note specifies no tap damage is permitted on taper surface. All the technical requirements for this unified special thread were easily completed with a stock standard thread mill and tool holding solution from EMUGE, along with CNC programming assistance. EMUGE stocks an industry-leading thread mill program with a broad range of advanced technology solutions for the most demanding threading applications, machinery types, and production requirements. Tooling solutions are offered in solid carbide and with exchangeable carbide inserts for screw thread sizes starting at number 0, metric M1, and any thread diameter above without restriction. EMUGE's technical support team can ensure a smooth and efficient transition into realizing the many benefits of high-performance thread milling.
Now I'm going to switch over and have our second presenter, Joe.
All right, thank you, Dennis. Welcome to the Tapmatic webinar on tips for tapping titanium. So Tapmatic is a company which is specialized in the design and manufacture of tapping attachments and tap holders for over 70 years now. And we're a US-based company in Post Falls, Idaho. So there's 5 topics that we wanted to cover today that would help everyone with become more comfortable with tapping titanium. So first, we'll look at what makes titanium difficult to tap, a checklist for good tapping, best practices when tapping titanium, benefits of the synchronous tap holder, and also a brief look at some alternatives to tapping. So what makes titanium difficult to tap? So if you look at the material properties of titanium, it has very high tensile strength, especially relative to its weight. It has a low elastic modulus, which means it likes to deform easily. It has very low thermal conductivity, and because of this, it's commonly used in aerospace and medical fields. And because of this low thermal conductivity, one of the main difficulties when tapping titanium is the heat does not easily transfer to the chip as it would when machining a standard steel. So this can cause problems with reduced tool life, and this is why coolant can become so important when tapping titanium. Due to its elastic memory, it has a tendency to want to return to its initial position when cut. It is prone to galling, can create problems with long stringy chips, and the material is also very expensive, meaning that you want to minimize any mistakes, especially on a last operation such as tapping. And this is a checklist for good tapping. This could apply to titanium, but also any tapping. First, before you even begin the tapping process, you want to make sure that your part is rigidly held against any rotation and upward movement. Just as important as the tapping process is the drilling process. The drill must be sharp to get a correct size. The drill selection should match your tap size. And you must have proper clearance for blind hole tapping which helps with chip evacuation, and also you would always want to avoid touching the bottom of the hole with your tap. Sharp tap is required. The geometry and construction should match your material, and this is especially important for titanium. Select a tap with the proper H limits to ensure the proper class of thread. And for speeds and feeds, we recommend using the parameters from your tap manufacturer for your material and thread size. Now, when tapping titanium specifically, we recommend machines with rigid tapping cycles. A rigid tapping cycle, the machine spindle rotation and feed rate are synchronized to match a specific thread pitch. As mentioned earlier, taps made for titanium are always preferred due to their advanced geometry and will give best results in this material. And the tap, again, must be sharp. The use of coolant is also very important. Oil immersion in the coolant helps with lubricity. High pressure through spindle coolant is recommended if available for chip evacuation. Must also have proper tool holding. A synchronous tap holder is recommended, along with the use of square drive tap collets, and if available, through spindle ready tap holders. More on the synchronous tap holders in a moment. Here is an example showing a square drive ER tap collet. When doing any tapping, especially materials such as titanium, it is essential to use a tap collet as opposed to a straight bore collet. Inside the collet, there is a square cutout which transfers the torque to the square of the tap. This prevents the tap from slipping in the spindle and will give best results. As we mentioned, rigid tapping is recommended. There are just mechanically, there's always going to be a slight discrepancy between the pitch of the tap and the synchronization of your machine. Even a small discrepancy between machine synchronization and tap pitch increases the axial load and torque. This reduces the tap life and thread quality. Especially for materials such as titanium, these extra forces on your tap can be catastrophic, leading in worst case to tap breakage. To combat this problem, Tapmatic developed a unique holder called the SynchroFlex 2. This holder provides a microaxial compensation, which greatly increases tap life and thread quality. With this flexure design, they are designed to work without ever being overstressed, as they are mechanically fixed to a safe limit. With this, customers can expect to tap up to millions of holes with the SynchroFlex holder. Another benefit of our SynchroFlex 2 holders is it features a balanced internal coolant system for pressures up to 80 bar. With our system, the holder does not extend under pressure, and there is no effect on the axial compensation. We offer a complete tapping program, the smallest being our SynchroFlex 5 with an ER8 spindle, all the way up to our largest holder, which is an ER50 output. Some alternatives to tapping titanium are thread milling, as previously mentioned by EMUGE. This is also recommended titanium for large thread sizes, or when tap breakage would be catastrophic to the loss of the part. For cold or roll forming, these are fluteless tools which compress the material by plastic deformation. It is not usually recommended for titanium due to the material's elastic memory and galling. However, this could be possible with very small thread sizes. For example, we had a customer utilizing a triple odd 120 tap roll forming in titanium with a SynchroFlex holder. They let us know that using these methods, they had not broken a tap. Thank you very much for attending our webinar, and let us know if you have any questions.
Thank you, Joe. So with that, we're going to take some questions from the audience. And we will begin with questions that we had leading up to this. We can open it up to either Mark or Joe. If either one of you would like to address whether roll form taps can be used for titanium. Who would like to tackle this first? Mark?
Yes, yeah, I can. We can use the roll forming method in titanium. However, there are many restrictions that were highlighted in both presentations. Generally, if we're talking about roll forming with titanium materials, we would typically be talking about smaller screw thread sizes, right? So we could be talking about 0.80s, number ones, 256, so forth. But as you get in larger diameter and coarser thread pitches, say we start getting into 3/8 16s, 7/16s, 14, half 13s, here the load becomes very, very problematic, and also the displacement of the material much more difficult because of the size of the chip section or the material section that we're dealing with. And then also that split crest at the minor diameter, which can be restricted in many components. That's it.
Joe, any thoughts?
Yeah, just to add on to what Mark was saying, normally we would never recommend a roll form for titanium either, except for where we had found it to be a benefit was in the very small sizes, such as that triple odd 120 application we mentioned. Another benefit of the roll form on the very small sizes is due to not having the cutting edges, it has a larger cross-sectional area, which makes the tap itself stronger than the same size cutting tap, which could lead to less chance of tap breakage on a miniature tap.
Well, the second question there is just, does microaxial compensation benefit rigid tapping applications? Joe, why don't you take this one?
Okay. So with a rigid tapping cycle, as we said in the webinar there, the machine spindle rotation and feed rate of the machine are synchronized to match a specific thread pitch. So in a perfect situation, the thread would be, perfect every time if the synchronization could be, perfect. But the reality is, no matter how new the machine, how good the machine, how good your encoders are on the spindle, there's always a very micro discrepancy between where the tap is and where the machine believes the tap is. So if you're using synchronous holders, they provide what we call micro compensation in the axial direction. So this just allows the tap to follow its own lead. And so it greatly reduces the axial forces on the tap, which gives you better thread life. And also on a material like titanium, reducing those forces can really help prevent tap breakage and give you a much better gauging thread if it's following its own lead.
Art, did you have anything that you'd want to, that previous question?
I can concur with Joe. We also have a recommendation and also a product that is designed with this minimal length compensation. It is extremely important to the tap is ground precisely with the pitch in the finishing process at the factory. And any deviation from this lead will get translated in some negative way. It could be excessive pressure on the tool that could lead to premature failure of the tool, lower tool life. It could lead to gauging issues. It's been well known. I may be showing my age, but back in the 1990s, when synchronous tapping was starting to take off in the machine tool industry, it was learned early on that these, although they were a major improvement over conventional tapping, did not solve all the answers of tracking the spindle and the slide precisely to the tap lead. So this is why it's important to have this separation from the spindle and the slide with these micro adjustments to make for these small errors.
Okay. Third question there is about the importance of lubricity when tapping titanium. Mark or Joe?
Yeah, I'll touch on that real quickly. The lubricity, when it comes to titanium, is absolutely critical when tapping. The challenge you have with the tap is we have full engagement of the tool throughout the cycle, and because of this elastic memory or compression onto the tool, it creates a lot of load, right? Torsional load, and this means we got to have the tool with a very slick surface to keep it moving smoothly throughout the entire cycle. If we have low lubricity characteristics, basically what happens is the tap will get overheated. The tap will basically significantly increase in its torsional loads, and it often leads to sudden breakage when we're dealing with low lubricity. If you have a situation where using, let's say, semi-synthetic coolants, where we may have a low concentration level, say under 10%, and we just don't have the option to bring in a higher oil concentration to the process, this is where thread milling can be an excellent option to get around this need for high lubrication with a machine tap, because here we can run with leaner concentrations of oil and have no negative effect on the performance of the tool because of the lower circumference engagement of the thread milling tool.
Okay. Go on to the next question. So if you could both take this one, if you could define the thread mill limitations and which is better, thread mill.
I'll just touch on this one briefly, because for us, we specialize more in the tapping process. But one of the main limitations for thread milling is there's only so small of a size that you're able to thread mill. So once you get down to the very small tap sizes, you're basically always going to be tapping it, the triple odds, the double odds, the odd 80s. That's one of the main limitations. And then also a lot of the time, the cycle time with tapping will be faster than thread milling.
Okay. Okay, well, if that's it, I'm gonna pass on one of the questions that came in from our audience. This one has to do, I think it's directed at Mark, but yeah, be positive. One of the slides that you presented that showed different taps available for J-style threads. This person is wondering if you could elaborate on that topic.
Oh, sure. Yeah, when it comes to J-series threads internal, there tends to be some confusion as to the thread form itself as it relates to the internal. When it comes to tapping, The only modification to the internal thread is at the minor diameter. So in the J series standard, the internal does not include a root radius. That's a misconception on the internal portion of that. The only thing that is modified in particular is the minor diameter, which is enlarged to make additional clearance for the enlarged root radius on the bolt. So in terms of the tap selection, I would use the same tap, whether I was producing, say, a quarter 28 UNF or a quarter 28 UNJF. The selection process would be the same, tap it through or a blind hole. The one condition is the pitch diameter limit or the class of fit must be to a 3B class, whether we're talking the AS 8879 standard or the B1.15 standard. That is one of the conditions that the 3B class of fit would be the standard. The standard also does not require that the tap be marked with UNJ in the description, because there's no modification of the thread form other than the minor, but the minor diameter is controlled by the drill, not the tap. So therefore, the tap would just be designated as, say, for example, a quarter 28 UNF-3B.
Okay. We did get another question in, and it's probably the last question we're going to be able to get to here because we're running out of time. But somebody just submitted something, a question just about, is work hardening is a problem, and would you recommend a plug or a bottom thread? I think this is for either one or both of you.
Well, when it comes to the work hardening, usually the work hardening process takes more place in the drilling operation. So that's why the hole preparation is critical, that we don't induce excessive heat that will cause some micro hardening of the minor, which then of course will create additional problems for the cutting operation of the tap. When it comes to full bottom threading, and I say full bottom, let's say in aerospace, it's not unusual to have thread requirements that must be within 1 pitch of the bottom. For a machine tap, that is very problematic because the chip load becomes extreme if we have to reduce the chamfer to extra short length of 1 pitch. Often what happens is if you must use tapping in that scenario, I often see people will start holes on a machine using a semi-bottoming chamfer, and then they'll modify a tap and then come back in by hand, because the challenge is 1, the excessive load on the tap, 2 is the accuracy in terms of controlling your depth, because of the issue where you have the acceleration and deceleration, and ultimately the point at which the tap is going to stop at the bottom without making contact. So thread milling, especially over the last 15 plus years, where we have now technology where we can do successfully thread milling in titanium Inconels and so forth, down to common sizes in aerospace like 1032s, quarter 28s, very, very efficiently. And a short lead on a thread mill is a non-issue. There's no change in performance of the tool if we need to bring it that tight to the bottom.
Okay.
And I would agree with Mark there. We'd always recommend kind of the longer chamfer on your tap that you can get away with when tapping titanium to keep the cutting forces down, because if you think about it, if you have, let's say, 5 leads of chamfer, each flank of the tap is doing a lot less force going through it. Whereas if you have a bottoming tap, and let's say you have two pitches, it's going to be significantly higher torsional forces on that tap. So it could definitely lead to breakage, and there's good alternatives to that, such as thread milling or coming back in, like Mark mentioned.
Okay. Well, we are running over time just a little bit, and so I want to make sure that let everyone know if you wanted to reach out and contact either our presenters or myself. Here's our contact information. I'll leave this on the screen for a bit so that you can either grab a screenshot or just jot down our contact information. And again, thanks everyone for attending today's webinar. It will be available shortly after today's webinar concludes in a video format. You'll likely get an email in a day to provide a link to that video. And I hope that everyone enjoyed this. It's a new approach that Cutting Tool Engineering is taking, trying to connect our print magazine feature editorial to a series of webinars throughout the year. We have another one set up for February on milling, and another that's going to be a full hour. And then in March, we have another Lunch and Learn 30-minute webinar. So with that, I will thank our presenters, Mark Hatch, Joe Gillillan, and appreciate your expertise and insight, and look forward to working with you again.
Thank you very much, Dennis.
Bye-bye.